In today's lesson, we have a couple of short but related topics to look at. The first of these is what we call the commutative property. Now, mathematicians have a habit of applying fancy names to things that seem pretty obvious when you actually think about it for a while. And this is definitely one of those. So don't let the name here, the commutative property, scare you too much. But let's get into what this means. Addition and multiplication are what we call commutative operations. Commutative. What this really means is if we take the numbers either side of addition or multiplication, we call these operands in mathematical language. What we can do with them is swap them, so they can be swapped, and doing that doesn't change the result. So if I wanted to write these rules down, or this rule down more algebraically, what I could say is that if I have two values, a and b, and I add them as a plus b like that, well, I can add them in the other order, b plus a, and I get the same result. So as an example of this, if I had the numbers 2 and 9, so I had 2 plus 9 like this, well, we know that's equal to 11, but also equal to 11 is this, 9 plus 2. So it doesn't matter what order we write those operands in, we get the same result. Same idea with multiplication. So if we multiply two values and we also multiply them in the reverse order, those are equivalent. We get the same result. So for instance, 4 times 5 is equal to 20, but also 5 times 4 is equal to 20. So those two multiplications with the reversed operands are the same. Now it's important to note that this property does not apply to subtraction or to division. Those operations are not commutative. However, we can sort of use the commutative property with subtraction, as long as we remember that subtraction is really just adding a negative value. So if I have a subtract b, remember that this is the same as a plus the negative of b. And now I can swap them because this is addition. So I would have negative b plus a. And this is a useful thing to remember, that anytime we have a negative number and we add something to it, it's exactly equivalent to having those values switched around with subtraction instead. So an example of that is if I have 7 take 3, that's equal to 4. But we could also get 4 by having negative 3 and adding 7. Okay, so that's the commutative property. The other thing that we want to talk about today is something we call combining like terms. So firstly, we need to define what like terms are. So like terms are terms, if you remember from last week we defined what terms were, but like terms are terms which are equivalent except for their coefficients. So if you remember, we said that terms have the constant multiplying part, we call those coefficients, but those are multiplying the variable parts of the term. So basically, like terms are like terms if they have matching variables. The coefficients don't have to be the same, but the variables do. When we have like terms within one expression, we can combine them. So these can be combined into a single term by adding their coefficients. So let's look at a handful of examples of this. And I'm going to pull up a visualization of this. Well, I will in a moment. I'll pull up a visualization of this expression. But let's take a look at it first. So we have 4x squared plus 5x squared. Take 8x plus 6x plus 7. Take 3. So this is quite complicated. So if we could simplify this expression, that would be nice. So we had something far less involved to deal with. Well, this is how we can actually visualize this expression. So you'll notice here that I have these squares which represent x squared. Now the reason they represent x squared is because if we say they have a width of x and a height of x, then their area is the result of multiplying those two values, x and x, which would be x squared. And here I have 1, 2, 3, 4 of them. So this represents 4 times x squared, so it's 4x squared. So this represents our first term in our expression. This is our next term here, where we have 5x squared, x squared. Our next term is take 8x. So here I have these boxes which represent x. In this case, they have a width of x and a height of 1, so their area is x. But they've turned red here because they represent a negative value. So here I have 1, 2, 3, 4, 5, 6, 7, 8 of those. So that's take 8x. These x rectangles here, they're not negative. And there's 6 of them, so that represents the next term, 6x. Then we have some unit squares here. So this is our 7. If you count them, there are 7 of them. And then we have 3 negative unit squares. So that's our take 3. Well, when we're combining our like terms, what we're wanting to do is rather than have separate terms, we want to combine as many of them as we can. So if I look at my first two terms here, instead of having 4x squareds and 5x squareds, if I group them together, I get a total of 9x squared. If I look at the terms with x, not x squared, x, because those are different. I mean, it involves the same variable, but the configuration of those variables are different. I can combine these together. And then my units, I can combine those together as well. Now, working at our total 4x squared, that's easy enough. We can just count them. There are 9 of them. The others are a little more complicated because there's negatives, but that's not too much for us to worry about. If you remember, a negative is the opposite value. So if you add a value and its opposite, they're going to cancel out and we'll get nothing. So if I look at these two boxes here at the top, negative x and x, those actually cancel out. So together they're worth nothing. Well, together they're worth 0, more specifically. In fact, these are 0, these are 0, these are 0, these are 0, and these are 0. So I can actually delete those because together they're all worth 0. And that leaves me with these two. I can do the same thing with my units. If I have 1 subtract 1, that's equal to 0. If I have 3 subtract 3, that's equal to 0. So I'm just left with 4 for my units. Okay, so we can write this down and we can actually write what we get as a result of combining our like terms. So I have 9x squared. It's my total number of x squareds. I have negative 2x, so I'm going to subtract 2x. And then I have 4 units, which I'm going to write as plus 4. So now my lengthier expression here has been simplified to this shorter expression here. Let's look at the next example. So this is 9xy take 2yx. Now these don't look like terms because this has an xy and this has a yx. But remember, when we were talking about the commutative property, we know that multiplication commutes. So we can write multiplication in a different order, like so, and it still has the same value. So really, this expression can be represented as this. So I have a rectangle here whose width is y and height is x, I believe the way it's defined here. And I have 9 of them here on the left, and I have -2 of them here on the right. If I combine these, remember if I match one with one, they'll cancel out with positive and negative. So I can cancel these, and that leaves me with these 7. So the result of this expression is that it is equal to 7xy. Now, our final example, we have this expression. So, if I pull that up, I have 3y, then I have 4y squared, and then I have -14y. Now, I can't combine my y squared with either my y or my -y. Those are not like terms. But remember, commutative property says that we can change the order of addition. In the case of this expression, I'm going to switch the order of my first two terms. So I'm going to write that as 4y squared plus 3y take 14y. Now, in terms of my algebra tile diagram, that is equivalent to just changing the order of my first two groups. So now I have switched them around. And then now I have two groups of tiles, two groups of y tiles specifically, that are next to each other, which means I can combine them together into a single group. Remember that if I have -y next to a y, those cancel out. So I can cancel out these three pairs and delete them. And that leaves me with -11y. So I can write that down. Now I didn't do anything with the 4y squared. Okay, that doesn't have a like term anywhere, so that just remains in our expression. But then I have take 11y, like so. And that's the general idea of combining like terms. We want to practice these a lot more because trying to identify which terms are like and which ones are not can take a little bit of practice. But that's okay, we'll get there. But main thing to keep in mind is this general idea is that we can take a complicated looking expression like this and still get something that, well, might be somewhat complicated, but doesn't involve as many terms, so it's much simpler.